Hey there. This is just a little add-on video to section 10.1. I'm going to use some parametric equations in our later work in chapter 10 for a certain curve called a cycloid. And some of you might be interested in where you might or how you might derive those parametric equations. So that's the purpose of this video. So we'll start with that question you're looking at there. Think about a point on a wheel, say a wheel sitting, the point maybe is the point touching the ground, and then the wheel starts to roll. Rolls along a horizontal surface without slipping. And the question is, well, what kind of path does that point follow? So you can pause this for a second, see if you can draw it. Can you imagine that? Like what is the life like for a point on your bicycle wheel as you roll along without slipping? All right. So I hope you drew something. That curve is called the cycloid. And my business here is to try to show you one way to derive the parametric equations of it. Let me show you a picture of a cycloid here as we're talking. In that little animation, the wheel there is colored in red, and I've kind of drawn a blue dot. That's the point I'm following. And as the wheel rolls, it gets around 3 full revolutions there. You get to see 3 arcs of what the cycloid curve is. So think of that point, that blue point. At every moment, it has an x coordinate, a y coordinate, and yeah, I want to determine what are those things. That's what parameterizing means. This is a geometrically defined curve, and I'm trying to say what are the x and y coordinates of that point as it rolls along there. We need to pick the parameter. What's a reasonable parameter to pick? Well, since the wheel is rolling, it's turning through angles. Let's see if we can't try to use that angle. That's a natural number that might be useful. So in this picture, what I've drawn is sort of 2 copies of this wheel. The one on the left side of the screen, it's got the blue point there at the origin in the coordinate system. So the wheel hasn't moved yet. Its center is at the point 0, r there. You can see it because the radius of this wheel is r. And that second wheel is, just imagine it, it's rolled a little bit, yeah? So it's turned through this angle T. So the blue point has sort of started to rise up. I've indicated there its coordinates are called x and y, and we're trying to say what those things are in terms of t. So we're going to use some right triangle trigonometry to answer that question. Let me just say something about the notation I'm going to use down here. This OT, O and T are points. So OT, I mean the segment between them, and if I put the absolute value bars, then I mean the length of that segment, okay? And I'm looking at this triangle PQC up there. So PQC, maybe I'll outline it in some bright color. So you're all looking at the same thing I am. That's the triangle PQC. And we know one of its side lengths is R. Yeah, that's the hypotenuse. Good. Okay, well, let's use some trigonometry on that triangle. The sine of that angle T the sine of the angle T is the ratio of the side opposite T to the side, or the hypotenuse rather. So the side opposite T, well, that's length PQ. The hypotenuse is PC. PC, we already said, was length R. And I want to solve that for PQ. I'll show you why when I slide down. But so PQ is R times the sine of T. And likewise, I'll skip the details here. You can look at the equations. CQ, the other side, the other leg of the triangle, is R times the cosine of T. Yeah. So if the sine and cosines look backwards because of where they are, look at the angle that I'm measuring, right? It's always relative to that angle. Good. Okay. So I've got the picture copied back down here. So how am I going to use those things? Well, I want to figure out what X is, right? So let me do this in a couple of different colors. Where is X? X is the X coordinate of P on the X axis. That's right about there. And so this distance I'm shading in that red color looks like it's the length is X. Now let me choose kind of a lighter color. This whole distance from O to T I can think of like that. And then there's one more distance that I'll draw in, say, this color, blue. All right. And those are, I'm just shading those like that to help us kind of understand this equation that I'm writing down here. This OT, that is the yellow one, minus PQ, that's the one that I shaded in blue, is equal to X. And that's kind of clear from the picture because the difference, that yellow segment, take away the blue segment, leaves the red segment, which is X. Okay, so that's what I mean by this first equation. I'm doing something similar for y here. I'll let you kind of think of the details, but you can look at the picture. CT, well, that's the whole length, the whole vertical length from C to T, minus CQ, that's the length of y in a similar reasoning. All right, so what about these second sets of equations here? Well, we've already kind of explained that PQ was r sine t, CQ was r cos t, so those make sense. CT equaling r, that makes sense because as this wheel rolls along, the distance from that point to the ground never changes. That's always equal to r. So what about this last term? What about this RT? Why does that equal OT? Well, if you think about what OT is, it's the distance that the wheel has rolled along the ground. And that distance is also equal to this arc, right? I mean, that's what you mean as a wheel rolls along a ground. The distance that you travel is the arc that's rolled through on the wheel. And that arc on a circle of radius r is r times the angle t measured in radians. So that's where the RT equals OT comes from. Algebraically rearranging those things and making them kind of look pretty on the eye for t greater than or equal to 0. Those parametric equations describe the cycloid. Equations like that for some radius that I chose is how I drew that animation that we looked at the top of the video. And yeah, we're going to use these cycloid equations in lots of our examples as we move through the rest of chapter 10. Thanks.